topic of today's video is going to be acid-base reactions, which are also known as neutralization reactions. Alright, so these are going to work in a very similar way to the precipitation reactions that we actually talked about today in class. But we're going to be dealing with different kinds of compounds, specifically acids and bases. Now, we've talked about these before in class, but I just want to reiterate a few things just in review. So we might remember that an acid is defined as a good source of hydrogen ion in solution. So structurally speaking, an acid is going to have hydrogen ion as part of its structure. So the hydrogen ion, or the H1+, will be coupled with an anion of some sort. For example, something like the chloride anion to make the acid HCl. And when these dissociate, they're going to dissociate just like all the other salts that we've talked about, such that we're going to end up getting each individual ion in solution with its respective charge. Alright, so any acid will dissociate to give us hydrogen ion in solution plus the corresponding anion. Now a base, in contrast, is going to be a combination of a cation and the hydroxide ion. And a base, when it dissociates, is going to be a good source of hydroxide ion in solution. Alright? So, we'll take a look at some simple dissociations of acids and bases first, just like we looked at dissociations of salts last time. See that it's exactly the same situation. So let's start with an acid like hydrochloric acid here. Hydrochloric acid, of course, is made up of H1+, chloride 1-. So when it dissociates in water, it's going to come apart to form its component ions, namely the hydrogen ion, H1+, and the chloride ion, Cl1-, both in aqueous solution, just like a regular salt. I can take a more sophisticated acid, such as an oxoacid like sulfuric acid here, do the very same thing. It's made up of hydrogen ion, and I got two of them to give me a 2+ charge to balance out the 2- charge that I would have on a sulfate ion here. Alright, so when this comes apart, it's going to dissociate into 2 hydrogen ions, okay, from here, and 1 sulfate ion, both in aqueous solution. So we can see in both of these cases, the acid dissociation is a good source of hydrogen ion in solution. What about bases? Well, bases are going to dissociate exactly the same way. So here I have a sodium 1+ and a hydroxide 1- for sodium hydroxide. When that dissociates into its component ions, I'm going to get sodium ion in aqueous solution, and I'm going to get hydroxide ion also in aqueous solution. There's a slightly more sophisticated example. This would be strontium hydroxide, which we know from our solubility rules is a soluble hydroxide. Alright, so I have strontium here, carrying a 2+ charge. To balance that out, since each hydroxide is a 1- charge, I have to have 2 hydroxides as part of the formula. Alright, so the 2+ and the 2- will cancel. Now, if we let that base dissociate into its component ions, obviously we're going to get strontium ion in solution, Sr2+, and we're going to get 2 units of hydroxide ion also in solution, each one carrying a 1- charge. Alright, so again, we can see that when a base dissociates, it's going to be a good source of hydroxide ion in solution. So let's take a look now at a simple example of a true neutralization reaction where an acid reacts with a base in solution. So let's pick our 2 simple acids and bases that we have. HCl is our very simple acid that we looked at, and sodium hydroxide is our very simple base that we looked at. Alright? Now, to predict the products of this reaction, we're going to treat it just like it would be a precipitation reaction. In other words, it's just another form of a double displacement reactions where basically everything comes apart and the ions exchange partners, just like we did in the case of a precipitation reaction. Alright, so remember, hydrogen carries a 1+ charge, chloride carries a 1- charge, sodium is 1+, hydroxide is 1-. Let's let these ions exchange partners with each other. When we do that, what we're going to make is going to be a salt, which is sodium chloride. Alright, that remains an aqueous solution. And I can charge balance that. Sodium is 1 plus, chloride is 1 minus, so I know that's properly charged balanced. And then if I let the hydrogen ion exchange partners, it's going to get together with the hydroxide ion, and I'm going to write that as HOH. Now you might actually recognize that as good old H2O or water. So I'm actually going to put an L there because I know that water itself is a liquid. All right? So in a sense, we're going to treat the water as if it were, in a sense, almost like a solid or precipitate. In other words, that's going to be the one associated molecule that we're going to form here, which is going to be the driving force for the formation of the product or forward progress of the reaction. It's the formation of water that we really care about. Okay? So now, let's make sure this thing is mass balanced. Obviously, we're charge balanced here. H is 1 plus, OH is 1 minus. Looks like this is a balanced reaction equation, actually as I have it shown. So, what I've just shown you here is the molecular equation or molecular reaction. So we can also do an ionic and a net ionic here. So let's do an ionic. Again, using the same sort of rules that we talked about before when we're dealing with precipitates. So essentially anything that I can dissociate into ions, I will. Anything that I have to leave associated, like the liquid water, I will leave that associated. All right, so obviously this guy breaks up. So I'm going to have an H1 plus. Again, this is recognized to be an aqueous solution. I'm going to get a Cl1 minus. Again, I'm breaking this up exactly as I did over here on the left-hand side of the board. I can break my base up, let it dissolve and dissociate. So I get an Na1 plus in aqueous solution, and I also get a hydroxide ion in aqueous solution. All right? Now, let that go to the other side. That's a soluble salt, so I can break it up into its component ions. So I'm going to get an Na1 plus aqueous here, and a Cl1 minus aqueous. Now, with regard to the water, that's a liquid. That's a molecule. I can't break this up. It's not really considered to be ionic, even though in a sense I treated it that way charge-wise here. It's actually a molecular species. Okay, so as a result, I'm going to leave it associated. So I'm just going to write it as H2O, liquid. So in a sense, that's the product that I'm forming here. Just like in the case of a precipitation reaction, I was forming a solid. Okay? So in the case of an acid-base reaction, what do we make? We make two products. We make a salt and liquid water. Okay, so that's the characteristic of an acid-base reaction. All right, so now if I want to get this to the net ionic equation, I'm going to treat this again as I normally would. I'm going to identify spectator ions and cancel them out. All right? So is H1 plus the same on both sides of the equation? No, it's not. It's hydrogen ion here. It's part of water over there. I can't treat it as a spectator. I'm going to leave it there. Chloride, however, is a spectator ion. It looks the same on both sides of the arrow. Sodium ion also looks the same on both sides of the arrow. Cancel it out as a spectator. But hydroxide ion, again, doesn't look the same. It's hydroxide ion here, and it's water on the right. Okay, so now, for my net ionic, I'm going to put the two ions together to form the water. So I have an H1 plus aqueous, coupled together with hydroxide ion, OH1 minus. And when I put it all together, I'm going to get my H2O. That's my water. All right? So, the nice thing about acid-base reactions is because the product you form is always going to be water, in that case, we can say that the net ionic equation is always going to be the same. So no matter what acid is reacting with what base, the important product we're going to make is water. So what that means is that the net ionic equation for any acid-base reaction is going to be H1 plus getting together with OH1 minus to form water. That's it. So we're going to take a look at a few more of these next time in class, and we're going to actually apply some stoichiometry to these in the form of some simple titration type problems. So we'll see you then.